A set is just a collection of objects called elements. We write a set with curly braces, for example A equals open brace 1, 2, 3 close brace. Union, a union B. All elements that are in or in B or both. Think of a basket that contains every fruit from basket A and every fruit from basket B symbolically. X is in a union B if and only if X is in A or X is in B. Intersection, a intersect B. All elements that are in both A and B at the same time. Imagine the set of people who speak both English and Spanish. Formally, X is in a intersect B if and only if X is in A and X is in B. Complement, a superscript C or a bar. All elements of a universal set U that are not in A if U is the set of all students in a school. A superscript C is the students who are not in Club A formally. X is in a C if and only if X is in U and X is not in A. These notations are used everywhere in discrete mathematics, computer science, and everyday reasoning about groups of objects. A Venn diagram is a picture that uses overlapping circles to show sets and their relationships. Each circle stands for a set. The area where circles overlap represents the intersection. The total area covered by a circle including overlaps represents the union, and the region outside a circle but inside the rectangle, the universal set, represents the complement. Example, draw two circles, one labeled students who play soccer S and the other students who play piano P. The overlapping part shows students who do both. The part of S that does not overlap with P is S set minus P, i.e., soccer players who don't play piano. The area of the rectangle that is not covered by either circle is the complement S union P superscript C, students who do neither activity. Interpreting Venn diagrams helps you translate a word problem into set notation quickly and verify results visually. Set operations follow the same algebraic laws as ordinary arithmetic, which makes them easy to manipulate. Commutative law, order does not matter. A union B equals B union A intersect B equals B intersect A analogy. Putting apples and oranges in a bag, it doesn't matter which fruit you drop first, the bag ends up with the same mixture. Associative law, grouping does not matter. Open parenthesis, a union B close parenthesis union C equals a union open parenthesis B union C close parenthesis. Open parenthesis, a intersect B close parenthesis intersect C equals a intersect open parenthesis B intersect C close parenthesis. Analogy, if three friends share toys, it doesn't matter whether the first two pool their toys first and then add the third friend's toys, or the second and third pool first. Everyone ends up with the same total set. Distributive law, union distributes over intersection and vice versa. A union open parenthesis B intersect C close parenthesis equals open parenthesis a union B close parenthesis intersect open parenthesis a union C close parenthesis. A intersect open parenthesis B union C close parenthesis equals open parenthesis a intersect B close parenthesis union open parenthesis a intersect C close parenthesis. Analogy, think of a security badge that grants access to any of two rooms union, but only if you also have a key card for the restricted floor intersection. Rearranging the checks does not change the final permission. De Morgan's laws connect union, intersection, and complement. They say, a union B complement equals a complement intersect B complement. A intersect B complement equals a complement union B complement. In words, the complement of A or B is the same as not A and not B, and the complement of A and B is not A or not B. Real-world analogy. Suppose a museum has two exhibitions, modern art, M, and ancient history. H. The set of visitors who did not see either exhibition is the same as the set of visitors who missed both exhibitions. This is the first law. Conversely, the visitors who missed both exhibitions are exactly those who missed at least one of them, the second law. These laws are essential when you need to rewrite a problem that involves none of or not both into a form that is easier to count or reason about. Explanation: the cardinality of A of a finite set A is the number of its elements. When sets overlap, we must avoid double counting. The key formula is the inclusion-exclusion principle for two sets. The cardinality of a union B equals the cardinality of A plus the cardinality of B minus the cardinality of an intersect B. If three sets are involved, the cardinality of a union B union C equals the cardinality of A plus the cardinality of B plus the cardinality of C minus the cardinality of an intersect B minus the cardinality of an intersect C minus the cardinality of B intersect C plus the cardinality of A intersect B intersect C. Example: a class has 20 students who play soccer, 15 who play basketball, and 8 who play both. The number who play at least one sport is 20 plus 15 minus 8 equals 27, but the class only has 30 students, so 3 play neither. When complements are involved, use the cardinality of a complement equals the cardinality of U minus the cardinality of A, where U is the universal set. Combining these rules lets you compute sizes of any combination of unions, intersections, and complements. There are two main ways to prove set identities. Element-wise direct proof. Show that an arbitrary element X belongs to the left-hand side if and only if it belongs to the right-hand side. This is done by assuming X is in the left-hand side, unpacking the definition using union, intersection, complement, and arriving at X is in the right-hand side, and then doing the reverse direction. Example: to prove a union open bracket B intersect C close bracket equals open bracket a union B close bracket intersect open bracket a union C close bracket. Start with let X be in a union open bracket B intersect C close bracket. Then either X is in A or X is in B and X is in C. In both cases, X ends up in open bracket a union B close bracket intersect open bracket a union C close bracket. The converse is similar. Algebraic using laws. Apply the commutative, associative, distributive, and De Morgan laws to transform one side into the other. This method is quicker once you are comfortable with the laws. Example: a intersect open bracket B union C close bracket equals open bracket a intersect B close bracket union open bracket a intersect C close bracket follows directly from the distributive law. Choosing the right style depends on the problem. Element-wise proofs are more rigorous for beginners. Algebraic proofs showcase the power of the set laws. Explanation: typical exam questions ask you to translate word problems into set notation, simplify, and maybe compute cardinalities. Below is a step-by-step template that works for most problems. 1. Identify the universal set U, for example, all students, all employees. 2. Define each given condition as a set. For example, F equals students who take French, M equals students who play music. 3. Write the asked region using union, intersection, and complement. 4. Draw a quick Venn diagram to visualize overlaps. 5. Apply the appropriate law, De Morgan, distributive, inclusion, exclusion to simplify. 6. If a number is required, plug in the given cardinalities and use the inclusion-exclusion formula. Sample problem: in a company, 40 employees know Python, 30 know Java, and 15 know both. How many know at least one of the two languages? The cardinality of P equals 40, the cardinality of J equals 30, the cardinality of P intersect J equals 15. Use the cardinality of P union J equals the cardinality of P plus the cardinality of J minus the cardinality of P intersect J equals 40 plus 30 minus 15 equals 55. If the company has 70 employees, then 55 know at least one language, and 70 minus 55 equals 15 know neither. Practice with these steps, and you will be comfortable with any set operation question on an exam. Explanation: even though the rules are simple, students often slip up. Forgetting the complements universe. Writing a complement without specifying U can lead to wrong answers, especially when U is not the set of all integers but something smaller like students in the class. Mixing up or and in everyday language or can be exclusive, but in set theory a union B is inclusive. Always check whether the problem means inclusive or exclusive. Double counting in cardinality. Leaving out the minus the cardinality of an intersect B term in the cardinality of a union B inflates the count. Misapplying De Morgan's laws. Remember the complement flips the operation, union to intersection. Writing the complement of the union of A and B equals a complement union B complement is a common error. Incorrect Venn diagram shading. Shade exactly the region described. Extra shading changes the set. Assuming associativity for complement. The complement of a complement equals A, but a complement union B complement is not the same as the complement of the union of A and B unless you apply De Morgan. Being aware of these pitfalls and double-checking each step, especially the universe and the logical connectors, will greatly reduce mistakes.